interacting with each other, that's a complex problem. So can we analytically solve it, or do we need computers? How big's the problem? Is Python sufficient, or do we need something a bit lower level like C++? So let's have this discussion. How do we think we might go about building this model? Lagrangian mechanics. If you were to minimize the enemy in a Lagrangian mechanics, you would just get one answer, right? The energy minimum. Because a dynamic model is not always at its energy minimum. Define a coordinate system for our model to exist in. Yeah, that's a good point. So are we going to use X and Y and Z, or are we going to use theta, the angular motion? Nope. That was spoilers. I've drawn the whole model. So one of the questions is, we've got this pendulum. Do we have any equations for it? For those of us who did physics at university, first year physics, do we have any equations for this pendulum? Can we solve it analytically? F equals ma. Yeah. Simple harmonic oscillator. That's interesting that Sophie said that, because I didn't say simple. So that's the difference. If we had a simple harmonic oscillator, absolutely we could solve it, no problem. And how complex a problem is this? Given what we did on Python this morning, do you think this is going to be a complex problem that'll take a long time? Or do you think a computer will just be able to whiz it like that? A harmonic oscillator, yes. Yeah, Wiki is, of course, the source of all knowledge, and you should definitely cite it. Iterative calculations. Yeah, Sophie, you're kind of right there, yeah. It's a lot quicker when it's not using dynamic memory allocation. Yeah, that's true. But C is just faster than Python anyway, just because it's compiled code. But usually, just as a rule of thumb, if you've got a loop within another loop, and usually that means particles interacting with each other, then Python's going to be a bit tricky, and you might want to use C. Because loops within loops get big quickly. So now we've all had this bit of discussion, let's move forwards. So the task that we've got in the next hour and 45 minutes, or if people get bored, if people aren't bored, maybe a bit longer, is to actually build this model. So if you feel comfortable building a model of a simple harmonic oscillator, if you already have experience in Python and are confident enough to do it, then by all means, go and shoot off and run ahead and do it on your own. But if not, I'm going to try and live code it with you, and we'll work together to see exactly what modeling is doing under the hood in general modeling programs. So we're going to do a dynamic model, and it's going to show us basically what molecular dynamics is doing under the hood. And we're going to use Python to do it. So here's a little bit of maths. Ethan said earlier, I think F equals ma, right? In the chat. So the first thing to do, obviously, if you're building a model, is to draw a diagram, which Lars saw on Wikipedia. So this is the model of the pendulum that I'm talking about. So it's got some mass on the end, it's got some length, some angle, which is there as well, and it's got some weight pulling it down. So for those of you who didn't do physics, you don't have to worry about this bit, but just think in your head that there's a pendulum that moves back and forward like this. For those who did do physics, you guys will know that the torque is equal to this vector crossed with that force. And so if I expand that, I'll get the second derivative of that angle is minus g over L sine theta, right? Where g is acceleration due to gravity and L is the length. The key here is that this is the model, okay? So this is a really important thing to realize. This equation is the model. The computational implementation of it is not the model. This is the model. The computer is just a tool that we're going to use to solve it, okay? So that's really key. The model that we're applying to this system is d2 theta by dt squared is equal to minus g on L times by sine theta. That's the model. So can we solve it? Well, if we assume the small angle approximation and get this second equation here, then yes, we can solve it. So if that's our model and we make the small angle approximation, if we only care about angles less than like 10 degrees, then this is the answer to that model. Okay? We don't need a computer to solve that model. We can just analytically solve it. So this is really, really key in like modeling theory. This is the model that we're using, and models can be analytically solved. It's just in modern physics and especially biophysics, not often can you analytically solve a model. It gets too complicated too quickly. But in general, you can analytically solve a model. And in quantum mechanics, you come across these sorts of models occasionally because everything's discrete. But for us, we want to keep that sine theta. We're not making the small angle approximation. This is not solvable analytically. You can solve it if you make the expansion to sine theta, but you've got to cut it off at some point. So in general, it's not solvable. So let's generalize it. We'll say that the that there should be an equal sign, not a minus sign. d2 theta by dt squared is just the rate of change of the angular speed, which is equal to the torque over the moment of inertia. It doesn't really matter. Numerically, I can expand that into this equation. So if I assume, for computational purposes, that this is not a perfect derivative, it's not a perfect instantaneous rate of change, but there's some small, tiny time step delta t over which it changes, then I can say that the speed, the angular speed after some delta t is equal to what it was before minus delta t times by the torque over the moment of inertia, okay? But then I can expand this into a derivative of theta after some small delta t. I can work out how my angle is going to change after some small amount of time. So if I was to start this model at some angle, after delta t of time, the new angle will be angular speed times time minus the torque divided by the moment of inertia times by delta t squared. So that's the time step squared. So that's Euler integration for those who've done numerical maths before. Computers can't deal with continuous mathematics. They can't do analytical maths very well. So we have to expand it numerically in order to solve it within a computer. But it's important to realize that this is not the model. This is the model. It's just a solution framework. This is how we're going to get to the answer. Not the model, it's simply the solution finding mechanism. So this gives me a way to put in an angle and get the next angle. But then I can put that angle in and get the next angle and put that angle in and get the next angle and keep going, keep going, keep going. And then eventually I'll get a trajectory. That makes sense, everybody? that make sense? Great. Charlotte says kind of. Lars says yes. Simon says yes. Okay. So Charlotte, feel free to keep messaging as we're going through it if anything doesn't become clear. But the idea is that the model is what we start with. The fact that we're solving the model with a computer is irrelevant. The model is the thing that we start with. The fact that we're using a computer is just because it's not analytically doable. So that's where we're going with this. Yeah, exactly. I didn't steal mine off Wikipedia, by the way, Lars. I made my own thing. So I'm going to send you all a piece of code. So this code is basically the answer. It's going to be quite complicated, but I want us to work through it together. Pendulum model master.py. So first thing I want everyone to do is I want you all to download this and run it in Python with these parameters. Oops. Thank you, God. So I think if you just try running it, it should have a usage message. So if you just run it with, if you do Python pendulum model underscore master, it should tell you what parameters it needs. So when someone's run it, let me know in the chat and we'll see where we are. Great. So it wants a start angle in degrees. Would you call this a finite difference method? Yes, in general, but yeah. Okay, so let's put some parameters in. I'm going to put a mass of, well, the mass doesn't matter is the point, but it's general enough. So I'm going to put a mass of 10 kilos in. I'm going to put a length of 1 in, because why not? And I'm going to run it for 100 seconds. Oh, it needs a start angle as well. Start angle 10, mass, length. So when you put the right parameters into this program, it should print out 3 graphs. It should show them one at a time on the screen. Am I sharing my screen?
Yes, yeah.
Yes. All right, yeah. So has everyone got some graphs popping up yet? That's cool. So I did So I wrote this in. So pendulum model underscore master.py. That's the start angle, the mass, the length, and the time I want it to run for. Let's do a quick sanity check. If I wanted to slow this model down, because it's quite a fast sine wave, how would I do it? If I wanted to slow the frequency of that pendulum down, increase M. Increase length, yes. So Jack, if you remember, the mass doesn't have anything to do with it. It's kind of a red herring. But increase length, yes. For now. So I'm going to increase the length by a factor of 10. So it's 10, 10, 10, 100 now. You can decrease gravity, Adam, but that's hard-coded into the script. If you want to do that, that's fine. The script assumes that we're on Earth. My simulation is planet dependent, actually, but ironically, we're going to be talking about that later. Why does mass not make a difference? It took Einstein to properly work that out, but it doesn't make a difference because the force that we're dealing with is gravity. If we were dealing with any other force than gravity, mass probably would matter. Yeah, exactly. Zach says. Exactly. So Lars has already noticed, if you start at exactly 180 degrees, you'll probably get a flat line. So notice that I used a start angle of 10 degrees. So what we've just seen there is equivalent to the small angle approximation. But if I start at like 179.9 degrees, something really daft. Check out what happens on my screen. Okay, so that's not a sine wave anymore. So what the physicists might have expected to come out because of what they did at first year is not what comes out when you move out of the small angle approximation. You get these extended bits on the top, where it slows right down because the pendulum's all the way at the top. All the way at the top. So that's the angle. The speed looks crazy. So the speed's 0 and then it spikes and then it comes back to 0 for a while and it spikes and comes back to 0 for a while. Spikes, comes back to 0 for a while. And the energy spikes and then spikes and drops down to 0, spikes, drops down to 0. This is the potential energy, by the way, not the kinetic energy, I think. So if you guys want to play around with that model for 5 minutes, that's fine. What we're going to do next is go through the code and understand what the model is doing. How do I know that that is what a pendulum behaves like, for example? How do I know that my code is working? That's what we're going to be doing. Is that okay, everyone?
Ben, unfortunately, for some reason, I seem to have lost the ability of creating forms now.
Oh, really?
I get the same Teams error. Like it randomly came up, and I restarted my Teams thingy.
Oh.
Didn't work. I still get that error. So.
Oh, that's really weird. It's okay about forms, I suppose. The recording also dropped out and then started itself again. So.
Yeah, I think it's just Teams being beta.
Well, there are 68 people here.
Yeah.
Oh no, 68 people invited. There's 37, 30, 39, 45. There's 42, so that's quite a lot. So when you guys are ready, open up that code in a text editor and have a look through it and tell me what you think's happening. I think I might leave it for like 10 minutes for you guys to have your own little look through the code. But what I want you to know is that in the code on line 92, it says main program starts here. Everything above that are basically functions, things that are only used when we need them. So the actual code starts at line 92. But yeah, have a look through the code, guys, and if there's anything in there that you don't understand, for example, class, type it into the chat and we'll discuss it. Adam says class. Should I not have used class? Shashank Adam says I shouldn't have used classes. Why does it say return minus? Oh, which line is that, Lars? That might be...
Return.
Oh, yeah, it's a negative. It's like -1 times. It's like a negative number. Does modeling in Python require the use of classes? Oh, God. No, not necessarily speaking. No, it doesn't, Peter. But it's just, for me, it's a more efficient way of doing it. And I think it makes it a bit more conceptual to get your head around. So, for example, it says in the code on line, hang on, where is it? Line. It says in the code on line 116, a pendulum equals some pendulum, right? So it gets you a pendulum object that you can then do things with. So I could say something like pendulum.increase angle, or pendulum.swing, or pendulum.increase mass. It just makes it a lot more compact. Does that make sense, Peter? Yes, it's just a lot more compact. It's called object-oriented programming if you've never come across it, but if you have, that's fine. So let's have a look. So there, it says, on line 155, for example, it says a pendulum.calculate gravitational torque. So the pendulum itself knows where it is, and it uses that to work out what the force is. Yeah. And you'll be, is it like a structure of functions? Yes. So if you've used C before, what are called structures or structs are like the precursors of class. So it's basically just in memory, in computer memory, it's what's called a data structure. Oh, there's quite a, yeah. So I've written in comments throughout the code, I think, things that should be, oh no, that was in another one. So yeah, the init function is initializing. That's just what the function's called, Adam, within Python. So on line, is it 155 yet? No. So on line 116, Adam, you see where it gets a pendulum and it puts theta naught, mass and length into it. Puts those into the init function. That's just what it's called within Python. Okay. And so for those other people, everywhere it says self dot this, self dot that, that just means that the variable is within the pendulum. So I can then use pendulum dot theta or pendulum dot theta naught. The variable itself is within pendulum, just like if I was to use numpy.py to get pi out of the numpy module. It's exactly the same. So everywhere it says self is because it's within this, what's called a data structure. So if I go back, someone said, what's object-oriented programming? Python is basically entirely object-oriented. So what it means is, I don't know the best way to explain it in a intuitive way. Do you know, Shashank? A good way to explain object-oriented programming in a intuitive way?
Well, if you look at any programming language, you would generally come across two kind of things. One would be functions, that is things that operate upon variables, and another would be variables themselves. Yeah. So you have functions and variables. And if you are, say, working in your textbook or in your notebook, you would keep them separate in a sense that you have values for your variables and you have your functions, and you combine them to get your answers. Now, in an object-oriented language, you try and club them together into a single entity so that it's easy to pass them around, to operate upon them. And to think of it as an object is basically a collection of functions and variables associated with it, which basically makes it easier to handle all of it when you are programming. So an object is like your notebook, and you can ask your notebook to add all the numbers that are inside it and get the answer. Yeah.
Another way of putting it is it's like a self-contained object. So imagine I had let's imagine I had a class called particle, and I said particle.move, and then I opened up some brackets and I gave it a translation vector. That particle would update its own position with that parameter, moving it forward. So conceptually, it's like having physical objects that do things. So it's an abstract way of coding where you can think about how things actually exist in the framework itself. Are the names
under? The answer is yes.
Yeah. Are the names init and self reserved for defining classes? What would happen if you tried to make a variable called self? Phil, you probably would be able to make a variable called self because Python allows you to do things like that. Some words you're just not allowed. But if you said, for example, no, I'm just going to write at the top here. If I said A equals self, you would be able to do that, but I strongly advise against it. Just imagine that these things like init and self, things that you use as part of Python itself, just imagine that they're reserved and not for use. If, for instance, you put self equals 2, I don't think you'd be able to do self equals 2.
You can. I just checked.
Can you do it?
Yeah, you can do it.
Don't do it, though.
Yeah, don't do it.
So in Python and in programming languages, there's there's a difference between what's called an L value and what's called an R value. So things on the left and right hand side of an equals sign. Ideally, you shouldn't be able to say self equals 2, right? But if you can do, well, just don't do it.
You mess up the expected behavior. That's the short answer.
Very, very unexpected behavior. Not enough. It wouldn't be unexpected enough to crash your computer or anything, but your program might crash. I see you subscribe to Pep8. I don't get it. So if for those people who are interested, I'm going to take us through the code starting at line 92. So we understand what's going on in the program itself. Hello?
Did you answer this question about line 147?
Oh, line 147, you have a for statement. Why does this end at line 180? Oh, no, I missed that completely. Oh, that's interesting. If you notice, Lars, everything is indented by exactly the same amount. That's how Python knows whether or not it's inside a for loop or an if statement. You indent it just by the same amount every line. Is that okay?
So does that mean, Ben, that if you take the indent away, it's no longer in the loop? It's that simple?
Yeah. So if you took the indent away halfway through that loop,
yeah,
it would complain because it would say, hang on, there's an indent on the line after this, but there's no for loop. So what is that? It would give you a syntax error.
Sure.
But if you took the last 4 lines and you know where it says store data?
Then it would just do them once after you do
them once right at the end. You would just get one data point exactly.
Okay. So loops get done by indentation, just by pressing tab.
Yeah, that is okay, but unexpected for someone used to C. I agree. Everything is in brackets within C. That's how it's done. In Python, it forces you to be, shall we say, have good handwriting, if you like. It forces you to have everything lined up properly so it's easy to read. Whereas in C, you can just write anything you want as long as it's in brackets. I'm going to start on line 92 now, and I'm going to move through the program. Okay. So main program starts here. I put that in comments. I put that in comments to remind myself that that's where the program starts. So the first thing it says is print intro. If we go up to the function called print intro, it just prints this out, right? So that's so that we know that this program has started. So it's just a bit of, it's useful, right? And it's here on my screen. It just makes it look nice. On the command line, it makes it look nice. I mean, we're limited in what we can do, but the next thing it does is it reads the command line arguments. Now, so you guys have seen this already. We read command line arguments earlier. So what I've done here is I've said if the number of command line arguments, so if length sys.argv is not exactly equal to 5, then print the help command and exit the program. So sys.exit just exits the program. So if I was to write Python, Pendulum model master and nothing else, it would print out some help. Maybe. There. So it's printed out usage. Now Python doesn't know how my program is supposed to work. So print help is a function that I wrote just to remind myself how it's to be used. Can you see that on line 77? That there is exactly what's printed out here. And it tells me how to use my own program. So if you were to write a Python program that was to read data from a file, you might write file name as one of your options. And then if the number of command line arguments was the wrong number, you would print that out, just so that other people using your program know how it works. If that makes sense. So once we know that we've got the command line arguments, we know that there are 5 of them because it's managed to get past this bit, we can start assigning them. So I say that theta naught is the start angle. That's the first command line argument. And I've turned it into a float. So I've turned it into a number. I also get the mass, the length, and the simulation time. So that's how long I want this thing to run for in seconds. If I'm going too fast for anyone, just stop me and type in the chat or turn your microphone on and ask me some questions. It then runs this next function, so check. So I've got this function called check args, and it takes all the arguments in, and then it returns them. So if I go up here and look at check args, it takes in these parameters, and whatever angle you put in, it turns it into radians. And if that angle happens to be outside of the range of minus pi to pi, it puts it in that range for you. If m is less than 0, it says mass cannot be less than 0. If L is less than 0, it says it can't be less than 0. And if your simulation time is less than 0, it says it can't be less than 0. So let's test if that's working, shall we? So if I make this minus 10 and then 10 and 100 again. Ah, so that's nice. So it tests that the mass cannot be less than 0, right? So for physical modeling, that's really important, because if someone gave you a mass that was less than 0, that would be bad, because it wouldn't work. What is everything doing? Come on, teams. So up to this point, we've printed out an intro, we've got the command line arguments, and we've turned them into something that can be used by our program. So now we need to get a pendulum. So this line gets an object called a pendulum. Now I'm going to go up here. The people in the chat who've been talking about object-oriented programming, you guys will possibly know that there is a thing up here called a pendulum. And I had to define it, and I had to define the methods that it can use, for example. But for those others who aren't that interested in the actual programming mechanics, understand that we have now got a pendulum object within this computer program. So imagine that, experimentally speaking, we've effectively just built an object that can now move backwards and forwards. And it has some mass, it has some length, and it has some angle that it starts at. And I say pendulum.print details. So if I go back up here, pendulum.print details printed this out. So at the start of my program, the first thing my program does is it says, okay, the start angle is about pi-ish. The mass is 10 and the length is 10. So that's good. That means I've got something that's working. The next thing I need to do is, here's where Matt said you've assumed that we're on the Earth. Yes, I have, because I said G equals 9.81. Now, what I could have done is I could have made G a command line argument if I wanted and put it up here. But for this particular program, I didn't want to do that, okay? So G is just hard coded in at 9.81. Then calculate the angular frequency, which is the square root of G over L, whatever. I then calculate a time step. So in the PowerPoint, oops, you know we have this delta T everywhere. Well, that's the numerical integration time step. So for those of you who have done maths or physics, you'll know that that's how we do numerical integration. That's how we move this thing through time, okay? Now, dt can technically be anything, but I've set it to this value so that it's what's known as numerically stable. So it doesn't really matter. This is to do with numerical maths, but I've set this value of dt so that my simulation doesn't just explode and give me ridiculous answers, okay? So I haven't got dt as an input parameter because it's not for the user to care about. I've calculated what dt needs to be given how fast this thing is moving, basically. So you don't have to worry about that. Just know that we need dt to move the simulation forward. So if I know how many time steps, if I know how long the simulation is moving, and I know the time step, I can work out how many steps I need for the simulation to run, right? So the total simulation time divided by the time step is the number of time steps that I'll be needing to do. And I've done a quick check here. If dt happens to be greater than that simulation time, then it exits again. It says dt cannot be less than the simulation time. So if you put a simulation time in here that was ridiculously small, then your computer program wouldn't be able to move it through time because there isn't enough time for it to move through. Does that make sense, everyone? So now I've initialized my structure. So from what, can I have some yeses in the chat? Does it make sense what this computer program has done up to this point? For the experimentalists among you, which is probably everyone, you can just imagine that you have just built a pendulum in a lab. That's exactly what I've done in this computer program. I've built a pendulum, it's got a length, it's got some mass, and I'm just about to let it do this. That's what's going to happen. So that's some yeses. Yep, great, that's awesome. So this is the part where we implement the model. So we need some data, right? We need times, we need angles, we need speeds, we need energies. That's what we need. So these square brackets are empty lists. Imagine in your head that you've got a container called times, and we need to fill that container with different points in time. So this is the Python language for that. Don't worry about it. It's just an empty list, and we're going to start filling that list in. In fact, we're going to fill it in immediately. So I'm going to say times.append. So append means add to the end of this list current time. And the current time was set up here as 0. Angles, angles.append. I've said it's the pendulum.theta times by 180 divided by pi. So I've basically added an angle, but in degrees instead of radians. Just because degrees is sort of easy to understand. Speeds, it's worked out the speed, so it's the angular speed again put into degrees. I could do that, Lars, you're exactly right, and that's better for memory purposes. But in this, I'm just going to keep growing the list as we move on. So I could do something like that actually, Lars, but I'm not going to do that. And also energies. So notice I've said here, energies.append, and inside there it says a pendulum.calculate kinetic energy. So that's a function inside there. So how does that work? Well, if I go up to calculate kinetic energy, it says turn 0.5 times the moment of inertia times by the angular speed squared. So that's basically a half mv squared, roughly speaking. So when I put that function into here, it just puts the return value in there. I could do this. So I could make that, assign it to this variable called energy, and then add energy to the list. But a little shorthand is you just don't even need to bother doing that. You can just put the function in there. But that's how we're going to update our data at each time step. And for those of you who've noticed, there's a time and there are 3 data points. There are 3 bits of data. So these are probably going to turn into our graphs at the end, right? So this is where we're going to begin our model or our simulation of the system. So I've said for step in numpy.a range, which we've seen before, from 0 to number of steps in step 1. So it's going to go 0, 1, 2, 3, 4, 5, all the way up to number of steps. First thing it's going to do is print out some user info. It says if step is a multiple of 100, print out some data. You don't want it printing out every step. You just want it printing out every now and then. So I said every 100 steps, print something out. So the first thing it's going to do is calculate all the forces, right? Or torques, whatever you like. So torque, that doesn't need to be there. I'll just leave it there. So torque equals a pendulum dot calculate gravitational torque. So it's going to calculate the torque from gravity for us, which is exactly what we need for this function here. So we need this torque value, and that's coming from gravity. So this torque, you can imagine it just being a force, but basically we need to calculate that. And I've said pendulum.calculate gravitational torque. So if I go up here, there's a function called calculate gravitational torque. And if you notice, it uses sine theta and not theta. So this is where the small angle approximation would be if we were making it. But as we're not, it's a sine function. This is what changes our model and allows it to be more sophisticated than simple harmonic motion. There are a couple of other functions actually that are commented out. Calculate viscous torque or calculate constant torque. I might put those back in later, but for now, let's just ignore them. Numerical integration is the next bit. So update the angular speed. So I've said the new angular speed is the old angular speed plus dt times torque divided by moment of inertia. So that is exactly this line here. Okay? That line there and this line here are the same. Except there's a minus. Is there a minus sign there? And there's a plus sign there. Oh, the minus sign's in the torque, right? Okay. So that minus sign there is just, it's inside this torque, which came from here. So don't worry about the minus sign. That line there and this line there are exactly the same. And just like that update angle, this line here, theta times dt multiplied by the old speed plus dt squared times torque over the moment of inertia, that line is this line. So what we're doing here is numerically integrating. So we're updating the angular speed and we're updating the angle itself. If that dt value was too big, and you can imagine it being so big that this pendulum's just whizzing round again and again and again, it would become what's called numerically unstable. dt needs to be small enough that we can resolve the motion, but I'm not going to get into that. dt is quite small. This bit just puts it back on the range from minus pi to pi, but it should never be called with any luck. And then we just increase the time. So we say that the time is just equal to time plus dt. So the new time is the old time plus the time step. And then we store the data again. And that's it. The for loop ends after that. So what this simulation program is, and this is true for molecular dynamics, it's true for any kinetic model you use. Any simulation or model that you use will have a for loop in it somewhere that just does something again and again and again and again and again and moves your system through time in some way. It'll update the speeds, it'll update the angles or maybe positions, it'll store all of the data, and then it'll just do it again. So when you see a computational model, the computer part, the computational part, is simply this. The model itself is the bit that we've already done. I'm going to keep going back to this because I think it's important. This is the model, effectively speaking. This is the model. All the computer program does is solves the model for you. So all this is doing is solving the model for us. We've already got the model. This is the solution mechanism. And then at the end of that, it's just plotting the graphs, which we already know. So plt.plot time and angles. Plt.x labels your x-axis. Plt.y labels your y-axis. Plt.show shows it. And plt.clf is clear figure, just wipes the figure of all graphs. So I can start plotting again. So you can see it plots time versus angle. It plots time versus speed. And it plots time versus energy. And then it says goodbye. That's the end of the program. So that was the walkthrough of this model. Does that make sense to everyone? And yes, we can have a short pause for a break. Yeah, I've been yapping for ages, but that was it. Does that model make sense to everybody? Great. So it's important that you guys know that whenever you run GROMACS or LAMPS or even density functional theory or any crazy model out there, the model is not what's in the computer program. The computer program just solves it for you, okay? So modelers in general have expertise in both solving and working out what these models need to be. So when you're talking about models in the future, I think it's useful to understand that designing a model between an experimentalist and a modeler or theoretician is it's a joint effort. We can't do it on our own. It's not like we go, a modeler won't just say, yes, it should be like this. And if your experiments don't say this, then you are wrong. It's not like that. It's a back and forth. If your experiments say something, my model implementation might be wrong. And it's a communicative effort. We both need to know what's going on so we can feed back. So yeah, let's have a break. Keep that rolling around in your mind. We'll have a break and we'll chat about it in the chat. So feel free to go get some coffee or some food or something. Let's come back at 3:15. I've got so many of these ASDA things. I'm addicted to them. I also hope I get a good break, Anders, but I'm just fueled. Yeah, I'm just fueled by coffee. I miss Opposite. I hope it hasn't gone bust. If there's anyone who's still here, by the way, and wants to ask some questions, I'm going to sit here. So just come into the chat and ask some questions.
I'll go and fetch coffee for myself as well.
Yeah. Have you got any questions? Oh, you can. So is class equivalent to an object? That's interesting, Ethan. No, a class isn't equivalent to an object. And the best way I can describe this to you is there a particular online game that you've played that has something called an instance? right? What game was it? It's just so I've got some language to use to explain what the difference is. Yeah. Well, MMOs have to have them, otherwise they'd never be able to run. No, I don't mean something happening instantly. RuneScape, I don't know how it works. I'm going to take World of Warcraft as an example, but RuneScape's the same. So if you're playing World of Warcraft and you go into a dungeon, Ethan, okay, you will be in that dungeon with 20 people, say, in some raiding party. But another raiding party could be in that exact same dungeon, but you'll never see them. So the dungeon that you are in, the specific one that you are in, is an object. But the dungeon template is a class. So every time a group of 20 people wants to go into that dungeon, World of Warcraft gives them what's called an instance of the class. Yeah, it's like a template. It gives them an instance, a single copy of that template that can then take values that they have. So whereas we have one pendulum here, I could define 50 pendulums and none of them would know about what each of them are doing. The angle of one wouldn't affect the angle of another unless I explicitly told them to. It's probably anything that's an online MMO, it'll have to be the same. So MMOs usually have one master thing that everybody is in, and then loads of individual little instances. So yeah, running the code creates an object using the class as a blueprint. Yeah, it does something like that, yeah. When you get into languages like C, you can do things called singleton classes, where there is only one of them in existence at all times. But I'm not going to get into that. In principle, when the code sees this line, Python's not pre-compiled, remember. When the code sees this line, it makes a copy of that template with these specific values. And also every value that says self in front of it. Does that make sense? Much thank. Sophie, yeah, it's probably the same for Guild Wars, but I have no idea how Guild Wars works, but there'll definitely be an instance. For games like Call of Duty, everything's an instance, so you're never online with everybody. So every time you load into a new map, that's an instance of a map template. But the weird thing about object-oriented programming is once you see it, once you use this example and recognize it and understand it, you'll start to see everything through that lens. Are you not sharing that instance with others in your team? In your dungeon example, yes, you are. So in the dungeon example, Ethan, the players become variables within the instance. So, you know, it'd be self.player1, self.player2, self.player3. Well, it wouldn't be player 1, player 2. It'd be a list of players, but you get the gist. But yeah, once you start seeing the world in object-oriented programming languages, you can't stop it. It's like a paradigm shift. It's really quite hard. So whilst I've got you all, does that make sense now? Why the pendulum? You can conceptualize it as a physical pendulum that you've got in a lab somewhere. I'm going to try and write a form, everyone. So if I crash, I'll come back. Yes. Just for those who care about data security, all of this poll data is going to get deleted at the end of this meeting. I'll just close the whole lot down. So don't worry about having your data stolen. I jokingly said to Lars earlier that he should take the time off today and go play Final Fantasy VII, and now he's not here.
Hey, Ben.
Hiya.
How did you manage to get that now?
Oh, because I'm pro. I don't know. It just stopped crashing for a while. I don't know. So here we are.
No. Maybe only one of us can do it, and since I couldn't do it. You were able to do it.
Yeah, definitely. I have no idea.
I can't do it now.
I have no idea.
Yeah.
But according to the top on this, I'm not even in the meeting. So,
Huh?
I mean, we do what we
Oh,
can.
wow.
I know. So at least it's not Zoom. That's all I'm saying. I have a go at Teams, but I should really be having a go at my laptop. It's really old and clunky. Teams is really good. I like it. Although if it wasn't for Microsoft products, I would have switched to Linux permanently a long time ago.
That's true for like only, let's say, limited to Microsoft Office.
Yeah, and Steam. Steam's not very good on Linux.
I actually stick to Office because there's this thing called Publisher.
Oh yeah, Publisher's good. I use Inkscape. I think a few other people in the chat will be using Inkscape, which is really, really good.
So earlier you said you didn't want to say anything about Macs. What is wrong with Macs at the moment? Because Macs used to have Linux background.
Yeah, did they though?
Well, I don't know.
It looks like they do, but
I never liked Macs, so you're talking to the wrong person.
No, Macs are really good for the best way I can describe it is like it's the difference between an Android phone and an iPhone. It's very locked down on a Mac. It's very hard to do new things.
Well, that's why I refuse to have Macs, because it's
disagree, Jack Henry. Disagree. They're not good for nothing.
They're good for spending lots of money for just having a slightly more curved edge of the computer.
Good for draining your breath. There's some Mac hatred here, but I'm not going to allow it because some people have Mac computers and they find them quite good. And Mac stuff interfaces all of your devices quite well. So given that we're all already selling our data 24/7, you might as well synchronize everything. Yeah, exactly. Charlotte's right. It is easy to use because you can't do anything to it, so it's not going to break. Windows is kind of in the middle, but the way someone described it to me once was Linux is like someone giving you a flat pack car and say, okay, here's a car, go and drive it. And they're like, well, you can drive it in theory. And I'm like, right, all right.
And Linux is also a good way to get around the admin rights at the university.
Well, yeah, well, we're not getting into that. I'm not getting into that. I'm supposed to be a research software, not an engineer, research software champion or some silly title. So
it's worth pointing out at this point that Ben has already got round the admin rights at the university.
Let's not talk about that. No, I've not got around the admin rights at the university. That's not true.
Well, one way to get around is to become a professor, but maybe that's a bit of a different way.
You say that.
That's the long way round, yeah.
Is it?
Yes, because I have admin rights because I do release some I do some sharing of C software that I've made, and now I have admin.
Even the IT staff don't have admin rights anymore, except the problem because it's a security risk. It's a security risk, and it's also bad for data reproducibility if you don't know what versions you've got on your computer. Sorry, I don't mean to disagree with you. Well, I do a bit. I half agree with the university on the admin rights thing, and I half disagree. But Linux does allow you to just tunnel through and not worry about all that. Sorry, I don't mean to aggressively argue, but it's quite a contentious topic in the entire university, isn't it? So. Surely a desktop should be left blank.
Well, it's the same as saying that a normal desk should be empty.
Oh, yeah. Jack Henry, all you really need to work a computer is this. You should just have a flashing line.
Yeah, but then everybody thinks you're a hacker.
This is all you need. Just pretend the rest of it's not even there. Okay, so how did everyone find like this modeling stuff? Because what I've tried to get across today is I didn't want to teach you Python in a day because that's never going to happen. And some people will have already done some Python and some people will have done no Python. So my aim was to take you all through what can be done with Python and then share with you a model implementation. So my idea of the day was to help you all understand what modeling is from like an underlying, like a bottom level perspective, so that if you were to go and do your own model, either use one or implement one that already exists, you'd know what to look for to check that it's working. You'd know what it was doing under the hood in general, not specifically, but just in general. And you'd also be comfortable, for example, just using a command line a little bit to investigate what's going on. Is that true? Does everyone feel like they've gotten a little bit of that today? I'm not doing a form for it. Just spam yeses and nos in the messages. Yes. 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 Ethan says yes. That's really good. That's what I was going for. So for the final like half an hour, 40 minutes or whatever, I'm not going to be doing any more coding. So you guys have got that script that I sent you, but I'm going to bundle all this together with the recordings and send those over anyway. So you guys will have everything today. I'll put it on OneDrive or something. So if you want to go and investigate the model Pendulum Master that I did, and uncomment those extra talks to see what they do, you might be interested in that, or you might want to just see if you can write your own model for something else. This should provide a template for you to do that, and plot some graphs and stuff like that if you so wish. But for the afternoon, or the last 40 minutes, I was going to talk a bit more about what modeling is in like a, I don't know, how modeling and experiment works together in sort of a fundamental scientific perspective. So it'll be a bit more of a conversation. So if you don't want to be here for that, there'll be no coding, there'll be no learning. Well, there'll be learning, but there'll be no like practical. So if you want to leave, feel free. It's nice to have you here during the day. If you've got any particular feedback, send me an email and I'll note it down. But if you are interested in learning a bit about what modeling properly is in terms of how it links to experiments and stuff, then stick around and we'll chat about that. Is that okay, everybody?
If I may add, if anyone decides to start Python programming or any programming from now on and comes across a problem, feel free to contact us.
Yeah, and at the University of Leeds, by the way, there's an unknown resource, the research computing staff. So there's research computing engineers, research computing champions, and Martin Callahan runs a team of just all of these people who work with the supercomputer. If you email anyone in that group, they'll be more than happy to help you, because they never get jobs anymore because all the jobs just get diverted through the new form to the wrong people. So if you were to email Martin Callahan, for example, or one of his staff with a computer problem, he'd probably be happy to help. So by all means do that. They'll teach you how to use the supercomputer and other stuff like that. And from the command line stuff you've already done, you'd probably be quite well equipped to learn how to use the supercomputer. And if you write supercomputer experience on your CV, it makes you sound like an absolute genius, even though it's not that difficult. So definitely go ahead and do that if you find the time, even just to run a for loop or something daft. It's really good. So anything else, Shashank?
Nah, not really. Just this,
okay?
Like advertised. Please feel free to contact.
Yeah, I do. Our emails will probably appear in the chat or something. Right, so here's the PowerPoint. The model. So we've talked about what the model is, and we've talked about what the, oh, hang on, question before we move on. There are regular HPC training modules. Yeah, they definitely are. They should get advertised on all the physics mailing lists, am I right? But if not, you can just Google University of Leeds HPC, which stands for High Performance Computing, and that'll take you to some link probably. Yeah, the HPC stuff is really, really interesting. Yeah. MNL. Right. Okay. So what I want to ask now is, what is modeling, right? Like in general, from a really philosophical perspective now, let's get into it. So Ethan, in the chat earlier, you jokingly said F equals MA, or maybe not jokingly. You said F equals MA was the model. Okay. Now, you weren't entirely wrong there, Ethan. That was really quite insightful, almost. So we had this. Can you all see my screen, by the way? I'm sure you still can. Yeah, I'm still sharing screens. Yeah, Ethan, congratulations. You can have a medal or something. Exactly. So this is the model that we all immediately went to if we did physics, or probably understood and can conceptualize if we've ever seen like a grandfather clock or something like that. We understand this model. Move backwards and forwards because the pendulum has some mass and it keeps pulling it downwards, right? Now, for the physicists among us, we'd use F equals ma to get this. And that took us to this equation. And that took us to these equations, right? But my question to you guys is F equals ma true? And I mean true in an absolute sense. So by all means, type in the chat, is F equals ma true for a given value of true? So I'm talking true as in philosophically true, as in we know it for 100% certain. Imagine if mass is constant and all that. Is F equals ma true? Just some yeses or nos in the chat would be interesting. It's not a question that there is an answer for, by the way. Yes. Question mark. Okay. Yes. Maybe. Maybe. I like the maybes. Yes, but it feels like it's a trick question. It's absolutely a trick question. Cognito ergo sum, everything else is supposition. Well, I think therefore I am presupposes that you exist, which is questionable. So if we're going to get into proper philosophy, I like what Adam said there. But definitely. So the maybes, and the yes question mark, the uncertainty there, I like that. Because if we go back into F equals ma, for those of you who did mechanics to a bit further level, and it doesn't matter if you haven't, just for now, just take my word on this. And another one, is this true because it's numerical, for example? Is this true? True in the philosophical sense, I don't know. But if we go even more fundamental, this is called the action. Okay, so for those of you who've never come across this, and this is anyone who hasn't done physics, and even in physics, anyone who hasn't done really advanced mechanics, this is called the action. And if I assume that variations in the action are equal to 0, so this cannot change with variations in A and B, i.e. the path, you get what are called the Euler-Lagrange equations. And if you put the value of L in, you will get F equals ma. So F equals ma is actually derived from something else. So my question to you now is this true? If F equals ma is actually derived from something even more fundamental, is the fundamental thing true? Yes or no? Is this true? If you've come across the action before, is that true? Is that the fundamental law of everything, minimizing the action? And if you've never heard about the action before, that's absolutely fine as well. So the point I want to make here, and this is sort of a paradigm shift, maybe, if you follow along with me. Could we not continue taking models? Rigorous mathematical proofing. Interesting. Could we not continue making models that take into account even smaller variations ad infinitum? That's interesting, Peter. Probably. is my thing. But I don't even know if I'm using probably right there. Jack Henry, to comment yes or no, I need to see rigorous mathematical proof. Okay, hypothetically speaking, Jack, if I could prove this led to this, would that mean that this is true? Or does this have to be derived? So the point I've made on the right-hand side, and this is my philosophical opinion. You have to define your own true. Do you see how interesting that is? And this is why I thought this was important today, because Peter's immediately gone to, you have to define your own true. That's very fake newsy. And that's not a bad thing. It's just something that we really need to keep in mind when we're doing science. Does that make sense? So I'm going to take you through how I sort of resolve this issue, how I resolve whether experiments are true or whether models are true, or whether they're both true. A model is true as long as it describes the data accurately. Lars, I agree with you the most, and I'm a theoretician. It's true as long as it describes the data accurately. But the data itself is only accurate if the equipment itself is accurate. And that was measured to be accurate by previous pieces of equipment. And it goes back and back and back and back until, I don't know, you've got cavemen chucking stones around, right? All models are wrong, but some are useful. Yes, but wrong implies that there is a binary state between wrong and right, whereas really there's a probability distribution, I think. So I like all this stuff. For me, as a theoretician, whilst all of these, they're all highly general. F equals ma for most physics. Yeah, Jack Henry, again, I agree with you there. If it gives meaning, that's interesting. I can't say yes or no to any of these. It's just thinking about them is important. Yeah, definitely. Whilst all these models are, whilst they're general, F equals ma is usually enough for any physics until you get to general relativity or quantum mechanics. And then you have to worrying about the action and quantizing the action and all this sort of stuff. But even this is only true because it fits empirically to measurements that we have made. They're all models. F equals ma is not true. True. At least empirically, it's not true. We're pretty damn sure that it describes 99.99999% of things, but it's not 100% true. And you only have to go to Einstein to know that. Newton thought that was true for all values of Fm and A. And Einstein came along and said, yeah, but what if you're really near the speed of light? And it turns out it's not true anymore. Or it is, but you have to mess around with some other things. And you go down to quantum mechanics and you say, yeah, but what if mass isn't a scalar, but an integer value of different units? Then what is F? It's not, you know, these are all models. And that's a real key idea. So when I was saying before that that mathematical equation was a model, it is a model. And to make that model, we have assumed that F equals ma is true, which it probably is, but it might not be. So we have to keep in mind, does more generalization, i.e. this top one, does that imply more truth? I don't know. Maybe. So there's an example that someone shared me recently. Does everyone know who Stephen Wolfram is, of Wolfram Alpha online? You can plot graphs and stuff in it. Okay. So if you were to go to Wolfram Alpha, you could say plot y equals e to the x, and it would just plot a graph and understand everything for you. He's a polymath who's tried to combine linguistics and mathematics. If you Google him, you'll find that he's currently trying to be the next person to make a theory of everything. And his theory of everything is that the universe that we exist in is computational. So what we see as continuous is actually just an emergent property of computer programming sort of behavior. So if you were to follow this link, you would find him talking about it. And if you were to follow this link, you'd find physicists being very angry that he's trying to do this, because that sort of thing's a bit philosophically touchy, if you like. But it's important to know that there are people who think that this, the numerical stuff right at the end, is the most true. And everything else is just an approximation of some computer program. Does that make sense, everybody? I know we're getting a bit airy-fairy, but I think this is important to understand whether or not modeling is real, because a lot of people come up to me and ask me to write a model as though I'm like a prophet and can just generate the answer. And that's not how it works. There is no revelation in the last 60 seconds. What, the Wolfram stuff? So Stephen, if you follow this link, you can find it. But Stephen Wolfram is trying to develop a discrete simulation, like he's trying to show that what we exist in basically a computer framework. So Sophie says, like how the analytical SHO was approximation of small angles, but the value with the first, second, third order terms was true for all cases with large angles. Yes, but you can keep generalizing, right? So you can go as far as you want. You can get any answer you want is basically the result of it. But from a scientific perspective, modeling's only true if it fits with experimental results, right? And vice versa. So modelling is about deriving upwards. An experimentalist is about inductive reasoning downwards. So it's like a deduction and an induction meeting in the middle. Does that make sense, everybody? That's how I see modelling and experimentalism. That makes it sound like a religion. Experimental stuff. And there it is, yeah. Adam Sweetman. Thank you. So I've got a bit of a case study on this that I thought I might share with you all because I find it quite interesting. Modeling's not a cult, except that it is. I'm about trying to prove simulation theory of the computation. No, he's trying to make, what Wolfram's trying to do is come up with an absolute fundamental unit of existence that is basically Turing complete and can explain everything that we see in the universe. So he's trying to come up with the ultimate quanta, if you like. I agree. It's very touch and go. But the reason I think it's very touch and go is because even if his model explained everything we see, it's only true until we measure something that disagrees with it. And then it's not true anymore. Just like Newton's gravity. As soon as Einstein came along and went, yeah, but what about gravitational lensing or whatever he did? It's wrong. So Newton's models, mathematical models, were wrong. Einstein's are probably wrong because they don't mesh with quantum mechanics properly, right? So they're only right within a certain reduced coordinate system. So I've got this example. That's just, yeah, right. Yeah, that's just some text. It don't really matter. I've put for a model's only useful. A model only has relevance within science with respect to how well it reproduces empirical observations. Otherwise, when you use that model to deduce something, it's wrong because the starting position that you're deducing from is incorrect, if that makes sense. So I put, for a wealth of examples, see any modern economics textbook which models people as rational decision makers and then assumes that the results of their models are true. Right? So I'm gonna do a little bit of a case study, right? Now this case study is just a passing interest of mine, right? It's nothing to do with the existence of God at all, because that's insane. But the example that I'm going to use tries to model different universes, and I'm going to explain to you why I think that's wrong, and then I'll just call an end to the day, and we can ponder on these things. So there's this idea that the universe is fine-tuned for life if you've never heard of this idea, it's the idea that not just sometimes the world, but more often that the universe is fine-tuned for life to exist within it. It's an old idea, but people have tried to do experiments to show that that is true. Okay, so they did the Miller-Urey experiment, right, which maybe had a different function, but effectively this is what they were trying to do. So if you've never come across this experiment before, they try to simulate within an experimental system the initial conditions of the universe. And their goal was to see what came out. And they left it for a long time. In fact, they left it basically in a cupboard. And when they came back to it years later, they found that rudimentary amino acids had formed out of the material that they'd put in there. So they'd effectively put in some raw peptides and saw that amino acid chains had formed. And then they said something like that shows that you can form life, life can evolve or whatever on this planet. But if you think about what that means, it means that we're just testing whether our model of the original conditions of the Earth is accurate by measuring evolution, which is kind of insane if you think about it. They did this experiment to see if life would come back given these initial conditions. But all they're doing there is checking whether their model of the initial conditions is right, which is kind of crazy. But they did it anyway. But it doesn't tell us anything about whether the universe is fine-tuned or even the Earth. It's a really specific set of things. So other people realized that you can't access other universes with the experimental procedures that we have available to us at the moment. So quantum mechanical interpretations aside, for all intents and purposes, we can't do an experiment that does not take place within this universe, right? So these people opted for a modeling approach, right? There's a very large 200-page paper on arXiv called The Degree of Fine-Tuning in Our Universe. And the conclusion of it says, is our universe maximally habitable? As in, they've run a simulation and of loads of different initial conditions and worked out whether or not our specific universe is maximally habitable, if you like, if it's the most likely. This, if you think about it, and others, implies that other universes even exist, which is an assumption at the moment. They don't know that that's true because it's never been measured. Not only that, this maximally habitable thing implies that there's a probability density running over different universes, which again is quite a big step. So what these modelers are doing is they're changing the values of the gravitational constant, G, the electron charge, E, the fine structure constant, alpha, and all these other parameters to see whether or not life can form or even a universe can form under those conditions, right? But if you think about what that means, and this is the end result, without experimental access to other universes, these models are doomed to fail, right? And I don't say that lightly. I say that because they have no reason to suppose that you can even vary any of those constants at all, okay? Can you even vary the gravitational constant? Well, yes, you can mathematically, but does that mean anything physically if those other universes have not been measured? Well, not really. And they've assumed that the limits are plus and minus infinity, which is also an assumption. And they've going further, they've assumed that what we would call the laws of physics, which earlier we saw are not laws, but models, these laws of physics, which I think is a really bad term, are not laws at all, they're approximations. Assumed that these things are constant between universes, which is also an assumption, right? So they're not doing a parameter sweep over any parameters that exist. They've just assumed that our universe is the same everywhere and only the constants change. So the point I want to make here is that if you have a value of G in our universe, n equals 1, right? So the average value of G is just G because there's only one of them. But the error on that value, if you've only got a finite number of universes, the error is infinite because you've got 1 minus 1, 0 on the bottom. So it's 1 divided by 0. So the error is infinite. So the point I'm trying to make with this is that models are only as good as the experiments that have been done to initially parameterize those models. And in this extreme example of universes, no one's ever measured a different universe experimentally, ever. So the error on this massive 200-page thesis thing is infinite on all values, because they've assumed that these values can vary. But the real value of n is 1. So all of their errors are just infinite. So this -1 thing that we all joke about when we're calculating standard deviations really matters for small n, because the point is if you've only got one value, your error shoots up to infinite because you can't know anything about its variance. So that's the takeaway that I just wanted to discuss with you all. Models can be used to guide and verify experiment. They can be used to guide it in the idea that they make predictions, and they can be used to verify it in the sense that they can use existing presuppositions to make the same conclusions, but they don't contain truth in and of themselves. They're as empirical as experiments are, and they're dependent on experimental input. So that is the conclusion of that crazy philosophical bit. But I wanted to share it with you because I think it's important to understand what modeling really is. Is that okay with everybody? And you can completely disagree with what I've just said, by the way. It's open-ended philosophy. There's a little book link at the bottom as to a suggestion for reading. But does that make sense to everybody, what modeling is, in my opinion? And how I think we should think about what modeling really is? And I mean, the reason I bring this up is partially selfish, because people come up to me and ask me if I can write a model that validates their results. And the answer is yes. Always. Because I can make a model do whatever you want. But that's not what we're doing. We're trying to do deduction through modeling and mathematics and induction through experiment to meet in the middle. I think that's a really important insight that we all have moving forwards. So, yeah. So that's the end of that. Yeah, The Principles of Mathematics by Bertrand Russell is probably the best text on this, where he describes computational classes, like Python classes, basically, about 50 years before they even existed. So it's a very, very good book. But in general, yeah, this is a summary. If you want to get into modeling, just learn a bit of Python so you understand how computers work, and learn the command line so you understand how to run models that already exist. But I'm going to read this out explicitly. Models verify and guide experiments and are publishable in their own right on that basis, but they don't contain empirical truth in and of themselves. So if you read a Nature paper, for example, that says we did these experiments that showed that this protein that we found is awesome, and we did these models to show that they're also awesome, have a look at what that model is doing, because if they've just dumped something into GROMACS without thinking about what that means, that's really important. And I'm sure Nature think about this, but maybe not as much as they should do. Model deductions are publishable because, mathematically speaking, numerical methods are deductive, just like an analytical derivation. So if I was to do a bit of maths that was analytic, numerically that's equivalent as long as my time step is small enough, subject to numerical error. But it must be remembered that they're only as good as their original experimental parameterization. And finally, it's important to plan out your model ahead of time and check if one already exists to answer your question. So don't be writing Python for 2 days and then find out that someone's already done it and published it for free. So I've done that many times, and it's embarrassing, to say the least. Oh, that's the end. Thank you. Any questions? I hope that was useful for you all. Round of applause. Thank you. Thank you, Ben. Oh, thank you, everybody. I really appreciate that. Yeah, I didn't want this to be like a crash course in how to do Python because there's so much of that on YouTube already. But yeah, great. If any of you could tell Lorna that I'm now unfireable, that'd be amazing. But you don't have to. This is completely free, no strings attached. But you know. The next Benamar is on the next lecture series. It's going to be it's going to be called "Why You're All Wrong." No, I don't know. If you find this sort of thing useful, then I can submit it to IT and share it with other people around the university. If you think that, do you think that'd be a good idea? I don't know. Because IT do these lecture series, right? Yeah, maybe I should do that. And it would be better if we all had access to an actual computer in the IT things, because I've got Linux slides as well. So when you get these slides, there's an intro to Linux as well. But whatever. Yeah, I can share the recording. We've been recording for 6 hours, so it'll be like a gigabyte. Yeah, the wider knowledge behind the raw code. Yeah, that's interesting, Jack, because the interesting thing is GROMACS does exactly what that pendulum model does. It's just well more complicated. Because if you think of atoms bonded together, they're all just simple harmonic oscillators connected by extra potentials, Leonard-Jones. But those potentials are just added in as extra force. Yeah. Yeah, so I've sort of put my entire day off to one side. So if anyone wants to stay and chat for a while about anything, coding or whatever, I'll be here until 5 or until there's no people left. So if you want to start dropping out now, absolutely go for it. Thanks for coming. I hope it's been useful. And thanks for engaging with the chat, because otherwise I'd feel like I was just talking to the void. No problem, Kalila. You get executive access because we have the same office. So, no problem. Why, thank you. No problem, Holly. Please let me win at things. What? Yeah, that's fair. Oh no, don't say 100%. That implies I can't win on my own merits. Shashank, are you still there?
Yeah, I am.
Thanks for helping out today.
No problem.
I really appreciate it. I mean, you were definitely involved at least half the time. Like,
yeah.
It was really good. Thank you for that. I really appreciate it.
No problem. I enjoyed it.
I'm glad. I'm very glad. I think everyone else did as well. I hope they did. I hope I didn't split the audience in half.
Oh, welcome.
Anders says thanks. Anders is there.
I think I will drop out as well, though.
Yeah, no worries. I'm sorry. I should have said and thank you to our assistants. I mean it sincerely. Thank you, and everyone else will probably mean it as well.
Yeah. Okay. See you then.
See you later. Give us an email if you want to chat about Python, just for fun.
Sorry, I was a bit too quick.
No, it's okay. I said give us an email if you want to chat about Python for fun.
Yeah, sure. I was thinking whether we maybe we can do something like a Python get together where people just drop in and do Python if they want to and discuss problems.
Yeah, that would be really quite good, actually. Yeah. Oh, there's some questions. Personal recommendation. There's a guy online, Adam. Oh, Jack Henry. Let's chat about object-oriented code in a bit. Adam, from a physics perspective, no. But from a pure Python perspective, there's a guy called the New Boston online whose tutorials are so cringeworthy you can't forget them. So that's my advice. Like, he makes jokes that are just not funny, and it's like, but then it's there forever. A crash course Python class. That would be interesting, actually, like a Python workshop.
Yeah, I would be up for that.
Yeah, let's organize that. I don't know if it will be online or in person, but I think if we had Teams going and we just rotated a screen share, that would be really good, especially if people other than us could help each other. That would be really good. Because once you learn how to use Python, for the people who are still here, it doesn't stop at physics. Like, I don't know, like if I want to, so let's say I illegally download comics, which I don't, right? But let's say that I did. I can automate that with Python by using web requests, by like doing internet searches from the command line. So that sort of stuff's really useful. You can reply to Twitter on Python. There's an import Twitter thing that you can use to tweet from the command line. Yeah, a lot of things are partially written in Python. Like, they call random functions here and there. A lot of things, actually, front ends are written in HTML now, just for the display. But the actual code that's run on the back is, yeah, Python. Jack Henry. Yeah, Jack, if you want to put the thing on, there's few people here now, so we can probably have actual chat rather than chat.
Hello.
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 Was that exactly what you thought it were going to be when you said, please help me do modeling?
I didn't know what to expect. It just sounded interesting.
That's the spirit. So, object-oriented coding.
Yeah, I think Sophie's question was quite good, like when it's appropriate, because I've never done it, and I've sort of seen people use it and ignored it.
Oh, I thought she just meant Python in general, but yeah, it says classes. Yeah, that's interesting. So your hardcore coders who are into computational theory, right, will quite often say that classes are bad because they make data structures that aren't readily parallelizable, right? And that's sort of true. But if you're just writing the odd bit of modeling software that you don't mind running overnight, for example, you don't want it to be super efficient. You just want it to be done and then leave it running. I think everything's better in object-oriented coding, just everything. So if you can imagine a physical object, like a solvent. Say you have a solvent with something immersed in it, right?
Yeah.
You want a class for solvent. And when solvent takes in something, it will apply forces to it that are consistent with the Poisson equation or whatever the solvent equations are. Do you see what I mean?
Yeah.
So if you can break your code down into like a solvent, some things that exist in that solvent, and usually a simulation box that gives you a universe with rigid lengths on it, I think that's a good way of doing it, personally.
So I mean, so you obviously seem to use it in modeling as like if you have a physical thing that you would touch that is like small,
yeah.
You seem to use that as like an object in Python. But when do you use it, like if you're doing like numerical analysis?
Yeah.
Would you ever use objects for that sort of code?
What do you mean by numerical analysis?
Say you've got like a massive 3D matrix and you plot images and stuff like that from it. So like more sort of not quite as complicated.
Yeah,
So,
but
yeah.
there I would. But there's for big stuff like that. There's and that's the physicist all over, right? Immediately letting it tend to infinity. In that case, you would have a class, in my opinion, and you would call it numerical analyzer. But that class would contain what are called pointers. And those pointers would point to specific locations in memory, okay, that were created somewhere else. So for example, say I have a system with 100,000 atoms in it. I would create a big block of memory that can hold everything I need about those atoms all in a big line, because then it's easy to access in the computer. And around that, I would create what's called a wrapper class that points to different locations in memory. Does that make sense, what I've just said? If not, it doesn't matter.
Sort of.
Because you've just gone to like, let's tend it to infinity. For big systems, classes are useful for humans. They're very useful for humans. But computers, their only class is memory. That's all they care about. They have a big class, it's called memory, and they just do stuff with it. That's what computers do. Add numbers up and stuff. So what you would do is just get a big load of memory, and you would do this in C or C++ usually. Get a big load of memory, and then create a separate class and have it point to different locations in memory. So you'd say particle 1.position is this location in memory. Particle 2.position is this location in memory. Does that make sense?
Is this memory mapping now, basically?
Yeah, basically.
Yeah.
Because what that means is you can do things like translation, rotation, and matrix diagonalization really quickly. But if you need to access specific bits of data, that will be slower, but you can still do it.
Oh, okay.
Does that make sense?
Yeah.
I mean, that's when you get, that's proper deep computing. You've immediately gone well beyond Python and into, and you can do this in Python, but it's quite hard.
Okay.
Yeah. But I just like object-oriented code because it's conceptually easy to understand.
So it's not efficient compared to just using like arrays and stuff like that.
No. So what the common like thing that people say is you want classes of arrays, not arrays of classes. So you don't want an array that contains loads of different classes if you can get away with it. You want a class that contains one massive array.
What do you mean by array of classes? Sort of define classes.
In Python, you know, I said pendulum in that last example. I got one pendulum.
Yeah.
I could make 1,000 of those and stick them in a big list and loop over that list and do stuff.
Okay.
So that's what I mean by an array of classes, a big list of classes that are all independent. Ideally, what you want is a big chunk of memory that you can do stuff to as a big chunk of memory. But then if you do have an array of classes, only use those very sparsely to access specific points of data. And within a computer, there's always a trade-off between speed and memory, because if you can store something in memory, you don't have to recalculate it. So there's a trade-off between whether or not these things are good. Does that make sense?
Yeah.
So what you probably didn't realize is everything in Python is a class.
Well, yeah, because the class looks a bit like a library to me.
Yeah, it is roughly, it is like a library, but it's a library that sort of, so NumPy, it's not really a class because you can't say, if I say NumPy.move, there's no value in NumPy that sort of changes. So NumPy is just a big container of things that you can just sort of get one at a time. But it is similar in its implementation. I agree. But yeah, I can't remember what I was going to say now. But object-oriented code is human readable, and from a physics perspective, it's understandable. From like a, you know, if I say pendulum.swing, I get what that's doing. And from a physicist's perspective, I might understand what the equations are behind pendulum.swing.
Yeah.
But if it wasn't called pendulum.swing, if it was called A open bracket 5 equals A open bracket 5 plus some sort of crazy equation, it's not human readable, so it's a bit hard.
Yeah, no, that sounds sounds like a good use of it.
Yeah, if you're doing something like NumPy, that library, behind NumPy, they've dealt with all that memory stuff. So if you build an array in NumPy or a matrix and say NumPy can you still see my screen?
Yeah.
Right. So I'm just going to write it here. It's not going to work, but there's a function called numpy.linalg.norm. Right. Linalg stands for exactly what you think it stands for, linear algebra. And whatever I put in there, it'll just give me the Euclidean norm of it. So if it's a vector, it'll give me the length. If it's a matrix, it'll give me the double contraction or whatever. So NumPy has all this memory management stuff in it for you already. So if you wanted to do crazy vector stuff, I'd use NumPy or SciPy because they're already there. But if you wanted to implement your own stuff, I'd use C. So.
Yeah, because I'm thinking like ways I could have like used objects now. Bits of coding I've done, but I didn't really know what they were.
No, definitely.
Bothered to learn about it.
Well, I'm 2 years into my 2 and a bit years into my postdoc now. I wrote a big piece of code called BioNet. It's quite good. It simulates network aggregation, right? But the memory structure, and it's too late now because I'd have to unpick it. But like the memory structure is awful. Like someone gave me a recent application of it, and I've been trying to do it for 2 weeks, and the memory structure is just god awful. If I had time, I'd start again, but I don't.
So when you say memory structure,
so it's not written in Python; it's written in C.
Right.
And the way it deals with memory is inefficient.
Okay.
So it's a big deal. So we're talking about 10,000 proteins in a box, and yeah, they're all spheres, but it's still 10,000 things interacting with each other. So if the memory structure is a bit off, every time you want those two things to talk to each other, it has to go somewhere else in memory, and it slows it down. See you, Anders. Have a lovely evening.
So you're not saying you don't have enough memory. You're saying the way it uses
it the way it's arrayed. Because like even my program that I've written, this BioNet grid thing, and even GROMACS only uses like, I don't know, a megabyte. It doesn't use much RAM at all. It's graphical things, GUIs that use RAM like crazy.
Right.
So if you ever have like Windows running slowly and struggling to open Windows, it's because that's a memory issue usually. But the programs that we'll write to analyze data very rarely use that sort of memory. So, yeah.
Yeah, so the reason I'm asking about memory stuff is because the software I use is called the Pro-Particle Model, and it basically runs out of memory.
Does
I
it?
sort of like, done small fudges like myself. But like I think I reached a point where basically like it got to like the Python code, which I don't know, and I'd left at that point. But that wasn't written very right. I think it was written to be CPU and like efficient.
Yeah.
And then it was obviously at the cost of being RAM expensive.
So what is it? What's in it?
So it's doing molecular mechanics, but it's only allowing one molecule to relax, and it's doing an AFM image simulation based on that.
Oh, that's really cool. So like how many particles are we talking?
So unit cell would be on the order of like
extremely high density data grids. That's where we run out of RAM. Yeah. The actual computation it's doing is kind of trivial.
Yeah.
But we're trying to store like Jack says, the way it does it is it stores its results in RAM basically. So if you an almost high density 3D data grid, that's when it runs out of RAM.
Yeah. So that's interesting. When we get into like when you're assigning memory, every time we made an array, it does it in the random access memory. It's not on the hard drive. Sometimes for big programs like that, like MD, it will keep a file open at all times, and it will get a certain amount of data memory in the RAM. And as soon as it doesn't need it, it'll just reallocate it to something else. And it keeps read-writing off the hard drive, but that's really slow. But sometimes if you need that sort of memory, that's what you've got to do. If it's running out of memory, it might be fragmented, but...
Well, I mean, the situation that ran out of memory was, this bit might be even Python, but we would take like an array, which something like 16 gigabytes, which admittedly is probably because it was using high precision floats, and then it would do a mathematical operation. Like, so it did like a convolution with a Gaussian, and that was the bit that was killing it in the end. And that just used like unbelievable amounts of RAM. I never quite figured out what point I was doing it.
Yeah, there's a couple of things it could be. Like memory fragmentation matters when you're pushing the limits, but also if you think about loops within loops, if you've got things interacting with each other like in 3D, you've got to build it's HD. It's more than HD if you think about it. The resolution that you might be trying to get might require more memory than you've got.
Yeah.
I mean, there's always the option of sticking more RAM in, but if it's in Python, so Python objects take more memory than do C objects. That's why Cython's there. So if I say in Python, if I ask for a number, maybe not a number, but like a list, for example, it's got all these extra things. So can you see my screen again?
Yeah.
No, not a pendulum. If I say A equals 1, 2, 3, 4, 5, right?
Yeah.
A is not just a container of 1, 2, 3, 4, and 5. I could say print A. I'm going to just do that, and then sys.exit. Because this isn't in a function, by the way, and is right at the top, it'll run it before anything else. Run it. So what dir does, you see I've said print dir A.
Yeah.
Dir doesn't just print out this list as it thinks it should be printed out. It prints out every function that's available to it. Oh, right, yeah, fine. Hey, why did it not do it? Oh, I know why. Let me just give me a minute and I'll show you what I mean.
So when you say function that's available to it, is that going back to classes and objects again?
Yeah, yes, basically everything's a class. So in C, you would not see this, right?
Okay.
But A is a list, and the list has a function add in case I want to add something to it, class in case I want to know what class it is, contains, delete attribute, delete item, blah, blah, blah. All these things with double underscores that you should never see. It's got append in case I need to add to it.
Yeah.
Clear in case I want to empty it, copy, count, right, all this stuff. It's insane. All I wanted was 5 numbers. Do you know what I mean?
Yeah.
And it's not 5 numbers, it's all this insane stuff. So Python's it overuses memory, but C, you should be all right with it.
Right, and so you know Cython.
Yeah, yes.
So is that an interface between Python and C++?
Yeah, so do you remember earlier I said that Python, when we type it at the command line, is a translator?
Yeah.
Well, Python can translate C as well. It knows what C commands look like. So you can write a Python script, and although Python runs it line by line, which it's not compiled, if you have a bit of Cython code in there, it will recognize that it's Cython code, and it will go look for some compiled thing that exists on your computer. So if you've got Cython code, you should have something that says something like Cython underscore x86 64 underscore Linux underscore blah, 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 all this stuff, .so if it's on Linux, or it's a compiled library, basically.
But so is it like another language you have to learn to write in, or is it something that like Python does for you, like Cython?
It's a bit in the middle. So in Cython, for example, I could say int a, and that would force a to be an integer. So a couldn't flip-flop around between being a float and being a double and all this. It's an integer, and that's it.
Right.
So if I say int a equals 5 and int b equals 7, and I say, and then compile it with Cython, and I say c equals a divided by b, c will equal 0. Because these are integers, they have to be integers. But if I left that out and didn't compile it with Cython, c would be 5/7 because it would upgrade them to floats. It would say, oh, these are floats now. It would dynamically allocate more memory for them, which is bad. And then it would, you know. So Cython just allows you to be a bit streamlined with it.
Okay.
But for memory issues like that, The University of Leeds, honestly, it has research software engineers. Have you come across them?
Well, I went to HRC training like 0 and 1, so I think yeah.
Yeah, there's a great guy. He sent me an email today. Actually, what's his name? Blah blah blah. Where is he? Alex Coleman. He works for the ArcLot. He's a research software engineer. He's got a background in, I want to say, biology something. But his job is for you to send him a request and him to help you with crazy code and stuff that's like perhaps beyond your current expertise, but you're interested in learning how to do.
That is, I didn't know that actually. That's really useful to know.
Definitely.
So like IT help, but above that. Yeah.
So if Alex Coleman, the guy's called, he works for the ArcLot. If you were to send him an email, he'd probably be like, "Where did you get this email?" And if you say me, he'd either be angry at me or not. But if you got in contact with him, I'm sure he'd be able to help you or point you in a better direction than the IT admin staff, who have got literally no idea what you're talking about.
Yeah.
So he'd be able to have a whiz through your code and say, yeah, your memory allocation needs this, that, and the other doing to it, for example.
That is useful to know.
If I ever get bored of research, I might do that, but I'm not bored yet.
Well, Shashank said that to me. He said that he preferred the also like the coding of getting like the coding behind setting up the simulation more than actual like analyzing the simulation data.
Not necessarily so. I might appear like that, but no, the whole is interesting. The whole line is interesting to me. So I work on protein hydrogels now. I do it because I'm interested in mesoscale biophysics. It's weird to me how we're not all dead, given that biology is so insane. I mean, that's my core interest, is what on earth is going on with biology. But I couldn't run a physical experiment for my life right now. Oh no, that's not true. Harry's left now, I think. He taught me how to run ISIS a little bit, which is kind of nice.
My PhD was meant to be like between the two, like experimental and theoretical.
So
then experiments haven't gone so well, so it's done more and more theoretical stuff.
Have you met Kalila?
Yeah.
Yeah, she's the same. She's in between. I like how in between means that you're expected to do both rather than half of each, you know? But whatever.
Yeah, Adam, half of each.
Or at least one thesis's worth of stuff.
Well, I mean, my theory behind it was with like our NC-AFM, so non-contact AFM, like the DFT sort of needed to understand the experiment.
Oh yeah, definitely. Like I say, it's meeting in the middle, right? Otherwise you've got no idea what's going on.
Yeah, it's like playing a mixed class in D&D. Yeah.
I don't know. I want to be able to at least like understand simulations behind it well, but it's a lot of work.
There's a lot of like for example, when you run GROMACS, a lot of people will just run GROMACS, and they'll just pick a random force field. A random force field. That's like saying, oh, I'm going to run this model, but I don't care what my parameters are, right? So it's helpful to understand, like, if you were to run molecular dynamics or anything, what am I telling this computer program to do, right? Well, it's a dynamical model, so I'm basically telling it to upgrade its positions in time. Well, how is it doing that? It needs to know all these spring constants of bonds and stuff. Where's it getting them from? And I think after this day now, people will think, hang on, they've run this simulation of molecular dynamics. How the hell did they know what the fluctuations in this covalent bond were? Like, how do they know that this binding site is real? You know, what assumptions have they made? So if a model makes a prediction and an experiment doesn't show that prediction, then the model's wrong, and vice versa, perhaps.
Yeah, this is a quite constant discussion in our group where it's like how much you're allowed to tune the model parameters to match the experiment.
Yeah, definitely.
Which seems to be like a skill of being able to know how far you can go before you're just trying to go, it's not real anymore. I just like fudged it.
That's exactly it. But there's like the point I wanted to get with the analytical stuff, right? Because The only difference between computer modeling and analytical deduction, right, like derivations and stuff, is that if you do it analytically, you've got a one-to-one function mapping, if you like. So getting really into math, you've got a list of inputs and a list of outputs, and you've got a one-to-one map between them, roughly. But it's no more true than a computational model. No more true than a computational model, subject to some numerical errors. So when you read papers about like the fundamental structure of the universe and stuff, and theoretical deductions of dark matter, this, that, and the other, well, unless it's been seen in experiment, it's not true. So when everyone was like, well, why did they do the Higgs boson? They already knew it was going to be there. And I'm like, well, no, they didn't. No, they did not. That's exactly the point.
They hoped it would be there.
They hoped it would be there because otherwise all of their modeling was wrong, and that's a waste of time, right? But if it wasn't there, the first thing that they would do would be to check the experiment was right. And the second thing that they would do is check that the modeling was right, because they both could equally be wrong in that case.
Yeah.
Definitely. If anyone's like modeling's true and other one's like experiment's true, the actual answer is neither of them are true. They're only true when they've met in the middle, which with mesoscale biology has not totally happened yet. With the stuff that has real experimental control like AFM, you can really validate stuff. But with like what I'm doing, how hydrogels form, well, Matt and Anders have to go all the way down to crazy beamlines to even have the slightest idea of what's going on, right? So there's a big gap in the middle.
So what is your like research at the moment? What are you modeling?
I'm currently trying to work out how protein hydrogels form, and whether or not, at the moment, I'm trying to work out whether or not it's got anything to do with how interaction sites are loaded onto the surface of proteins, or the stiffness of proteins, or whether or not they can unfold. Which is more likely to be the dominant factor in both how they form and then what their resultant elastic behavior is.
So like how far down are you going? So you're not doing DFT, are you? You're not
No.
No, you're not into the Schrodinger's equation.
No, so my proteins are spheres and ellipses at a push. Amino acid chains are springs.
Right.
But alpha helices, like single alpha helices and things with a bit of rigidity, are basically worm-like chains.
So you're not even doing individual atoms.
No.
Approximating like a whole molecule to be something simpler.
Yeah, because if I was to introduce atoms, there'd be no way to run the program. There'd be no way to do it. So that's a necessary.
What, as in the computer's not like?
Yeah, the computer wouldn't be able to do it. Not because there's not enough memory, but because if I introduce atoms, right, I have to care about time scales that are smaller than protein diffusion, say.
Okay.
But protein diffusion takes place over massive time scales, like hundreds of microseconds, tens of microseconds, more than that. So if my minimum time step and my maximum time length are too far apart from one another, the simulation cannot be done.
Your minimum time step.
Yeah. So if your time step has a numerical limit, right?
Why?
Because otherwise, so do you remember doing numerical integration?
Yeah.
Well, if you make your numerical integration time step too big, it deviates from the graph. It goes chaotic.
Oh, yes.
So
yeah,
there are ways around it, but there's always a limit. There's always a time scale in the system for which you have to have a time scale smaller than it in your computer program. There always is. And you can show numerically that it'll go unstable. It's an interesting proof.
So is that almost an argument to like validate not modeling it on that level because the atom jiggling doesn't matter, right?
Yeah. What you can't say is it doesn't matter. What you can say is I can't do it, but the assumption I've made is that anything on a length scale less than this, I'm not caring about it. I can't care about it. Because I don't have the computer power available or the time to develop it, for example. So the modern way of doing this, by the way, is to just throw more computer programming at it, right? So what you do now is just get 1 million GPUs in parallel. But that's not very scientific because eventually you'll just come to machine learning, where you don't really know what's going on. You've just got input and output variables and some connection between them that you don't know what it is.
Well, so you're saying the modern way would be you do simulate it on the atom level, but you just keep adding power to let you do it.
Yeah. So like there's a guy called, what's his name now? He used to be Barack Obama's scientific advisor. He invented a piece of hardware called Anton that was built specifically for molecular dynamics simulations. So it had hardware memory structures built for MD, and that meant it could run faster. So he could get atomistic detail up to microseconds, right?
Wow.
But eventually what you're doing is just including superfluous detail, right? So I'm sat down on my sofa now, right? But do I care where all the atoms are?
No, it's good. Yeah.
Because empirically, every time I've sat on this sofa, I haven't fallen through it. So the empirical reasoning I've done in my life says that if I sit on this sofa, I'll be okay. And it's the same with modeling. Eventually, there will be a length scale for which you don't need to care what's happening at a lower length scale than that. And I don't know what that length scale is. But for proteins, I'm assuming at the moment that individual atoms don't matter. If that makes sense.
But I would have thought, wouldn't it matter in like where the proteins are?
Oh, absolutely.
I'm not very good at biology here.
Yeah, you're absolutely right. So what I've done is I've got a sphere with explicit binding sites on them. But those binding sites don't move. There's no dynamics associated with them. If the sphere rotates, the binding sites rotate with them. It's a rigid constraint, so there's no dynamical behavior there. So that's one of the ways around time steps, is to just make it rigid. Because then you're not worrying about its dynamic motion, you just ignore it. So have you ever come across like coarse-grained models?
No.
So like if you move from atomistic, the next one up is called the Martini model, which is where you just assume that everything is its backbone carbon atom with some charge. What you've assumed there is that fluctuations in your side chains don't matter much.
So you're ignoring all the hydrogens.
Yeah, you've just made it effectively. You've turned your entire side chain into a big sphere that doesn't deform. So your new timescale that you have to care about is motion between spheres, not within them. So that's coarse graining. That allows you to bypass the timescale limit, if that makes sense.
Yeah, no, it's interesting because one of the things I keep thinking about more is like we do really small things and other people do like very similar techniques on bigger scales. And it's almost like how do you sort of, it's hard to, once you've done the really detailed stuff, how do you peel away the bits of like detail you don't need if you want
definitely
bigger?
The way to properly do it in principle is to run the entire system atomistically. And if it turns out that fluctuations in the atoms are decorrelated from anything that you care about, then just ignore them.
Isn't there a kind of like correspondence? You kind of like run the biggest system that you can, and then you look at running that same system using the coarser simulation, and they should correspond within error. And at that point, you kind of, and so then at each stage you go, okay, so I do this one, and then I match it with this one, and then I do the biggest one of that one that I can. I do the smallest one of this one.
Yeah, definitely.
And there's like kind of a chain of trust that's meant to build.
Yeah, definitely. But if you look at it deductively, there is actually gaps in that chain. But you're absolutely right. So what I did for my stuff is I ran an initial model of my protein through MD, just on its own, not in the network, and it was spherical, so none of the binding sites that I cared about were moving with respect to each other on the same level as the length of the sphere itself. So that justified me in ignoring them, right? And just said that they're rigid on the surface of the sphere. But what I didn't do was run the entire network atomistically. So I've assumed that the motion of that protein on its own is the same as the motion of the protein connected to the network, which might not be true. But I simply don't have the computational power to check it. And Lorna bought me a big computer, like a big ass computer, and I still don't have the computational power.
So why are you not using the HPC for this stuff?
I am, but I've got a local GPU that's faster than like 100 cores in parallel, so why do I even need to?
Oh. Yeah, because I remember you told me.
Use the GPU nodes on the HPC.
I mean, I could do, right? But like, there's a big queue. I've got my own.
Yeah.
And you can buy your own parts of the GPU if you want. You can buy a GPU node if you've got 20 grand spare, and they'll even maintain it for you.
Oh yeah, I tried to get some money to do for us because we primarily do DFT. GPUs aren't so useful as far as I understand at the moment.
Yeah.
But yeah, we tried to get some money for our own cluster, but it didn't work out.
Yeah. I mean, it's worth putting in the application, but unless you're like working on coronavirus, good luck.
So this is a bit off topic now, but why are the GPUs good for the molecular dynamics simulations?
So imagine you've got a GPU. Just imagine scaling it up, right? So it says, so your molecular dynamics system is the same size as the GPU memory card.
Okay.
But
you can flatten your entire system onto that GPU, and GPUs are built to be good at parallelized things.
But
Yeah.
I think the things there's certain types. I know very little, but there's certain types of isn't it something to do with whether they can be vectorized?
Yeah.
Or something. If at this point I'm just saying words rather than really understanding what they mean. But like if the problems can be vectorized, then they can be run very effectively on GPUs.
Yeah.
If they can't, they can't.
Yeah.
And it turns out that the molecular dynamics can be well vectorized, and as far as I understand it from my zero knowledge, like DFT can't be at the moment.
Yeah, it's because DFT, from what I understand, is at the very least it's n squared log n, right? But it's definitely not anything less than n squared, which is bad. Whereas MD in principle is n squared.
I think some of the codes are actually better than n squared now. I think Jack was probably there. I think Shashank was saying like some of them are better than n squared.
Really?
I can't remember what he said for FHA aims.
That's pretty amazing. But like, there's some serious approximations being made there, mean field stuff, if that's the case. But okay, that's
we'll
fine.
we'll have to get Shashank back in the conversation and find out one day. But
I mean, I thought the point of DFT is you're trying to not make as many approximations, so it's always going to scale badly.
Is that true? I don't know about DFT.
But I thought that's I mean, we're trying to get as close to solving the Schrödinger equation without breaking computers as possible.
Yeah, but the first thing it does is assumes that the ground state is the only state, which is not true.
I think it depends what kind of problem you're trying to solve. Like there's a thing like it's not just what like the sophistication of like the individual interaction you're trying to solve, but because you can have quite simple interactions that still don't scale very well as you add more particles, right?
Yeah.
It's not. There's two problems.
Yeah.
I don't know enough about this. I'm a stupid experimentalist.
No. It's not. It's not at all. It's just different skills, right? It's different skill set. But what you can imagine is if you imagine a square grid, like that's, I don't know, 256 by 256. Roughly speaking, GPUs can add rows together very quickly. And they can add local things together very quickly. And the MD algorithms just map onto that quite well.
So I've just gone on to FHIM's website and I've found this, which I'm going to post in the chat, which may be what we were talking about in terms of the scaling. That's like one of the listed features for it.
Hartree Fock. Linear scaling?
I don't know if that's like a very small subsection of like the DFT code, or is that the actual... I can't remember. I need to do my DFT reading at some point.
So linear scaling means if you double the number of cores, you double the speed of your simulation, roughly speaking.
Or if you double the number of atoms, you double the amount of time it takes.
Right?
Yeah. I mean, they're not always exactly the same, but yeah. Let's just assume that they're the same.
But I don't know if that's like a very simple form of DFT that FHIMs can do with that, whether that's...
At this point, we need to shank in the conversation.
Yeah. I can't talk to you further about this. But from what I understood, you're effectively doing matrix diagonalizations in DFT, which is n cubed. And if you parallelize that, it's n squared log n. That's as far as my knowledge takes me.
More knowledge than I have.
But that's amazing. I mean, they do QMMM as well, which is the combination of both. But that's basically just limited by the DFT bit. So QMMM is a mix of both, but you're just limited by the DFT bit, really. So that's really interesting.
Anyway, guys, I'm going to have to jump off, but thanks again, Ben.
It's no problem. I'm going to bundle all this together and put it on OneDrive or something. So if it was interesting, do share it around and stuff.
Yeah.
And pass me your grant code, and I'll charge £1,000 to it or whatever. I'm joking. Don't do that. Don't do that. That was a joke. That was a joke. Disclaimer. I'm not being serious.
All right.
Right. Sorry, I'll get ahead off, but I'll mute myself and go.
All right.
Okay. Cheers, guys.
So going back to the GPU stuff. So what's the difference between using a GPU and just using like 100 CPUs?
How the memory's laid out. That's the only difference, is how the memory's laid out.
They don't share the same memory, right?
So CPUs are, you can imagine. So GPUs are just hardware specific for doing parallel things, right? Okay. So when you want to render graphics, the thing at the top left doesn't care about the thing at the bottom right.
Yeah.
It does if you're doing ray tracing and stuff, but in principle, it actually doesn't, because each pixel can do ray tracing individually. And so it's super parallelized. GPUs were built such that you can just send in a massive array of pixels and it will just do all of those calculations in pure parallel behavior. But not only that, if they do need to communicate with each other, the way the memory's laid out is super efficient so that they can just be like whizzing communication. So if two pixels are close together, they can check whether or not they're the same value, like instantly, faster than a CPU can, just because of how the memory's laid out.
So how are MD calculations parallelizing? Because at some point, right, the atom has to know where the other atoms are, and they're all going to move as well.
Yeah, so the way it does it is, if you imagine a simulation box, just a big cube in space with stuff in it. Yeah?
Yeah.
Cut that box up into smaller boxes, like 100 on each edge, or 50 on each edge.
Okay.
That's called the cutoff length, those box widths, and that's usually set to be the electrostatic cutoff, so the Debye length. So beyond that, you're saying beyond that length, you're saying particles don't know about each other.
Right.
And if you think about what that means, it means that each simulation box component only needs to know about its neighbors. So every single step, what you do is you assign all of your atoms a simulation box or a voxel that they're a member of.
Okay.
So you dump them in the voxels, and then you loop over the voxels instead of the atoms. Because then the voxels only need to talk to their neighbors. So the top left one doesn't need to talk to the bottom right one. And that is exactly why they're good for GPUs, because a voxel is a three-dimensional pixel. It's exactly the same.
But aren't they still connected in some way? Because technically, if you change something in the top left, it could affect the bottom right.
Yeah, like, but not immediately. It will affect it because computers are discrete. They move in discrete time steps, right?
Yeah.
So if one affects its neighbor, then that will then affect its neighbor, and it will affect its neighbor, but it can only do that after a time step, right? And unless your interactions are moving at the speed of light, which I don't think they are.
Yeah.
I think you'll be all right. So as long as they connect to their neighbors, then you can get waves moving. But
yeah,
those waves will never be smaller than your individual voxel length, right? So that Debye length is really important.
Okay.
So it communicates, but it takes a while for it to get there, and that doesn't mean it's not physical.
Yeah.
If you've got your electrostatic cutoff length correct, then pair-pair interactions will be right. So if you have a pair-pair interaction that moves this one over here, then that one will now interact with that one and it'll move it over there. So it builds up on it.
Yeah, I find how these softwares, like, because you'll give them an input geometry and then they'll give you an output geometry, and it's done something in between. It's interesting, like,
yeah, how
what it's doing in between isn't necessarily physically realistic. And
no.
I learned this when I was watching my DFT simulation. And you could watch the C60 approaching the surface, and you're like, oh, that looks like, if you were to like fire at it, sort of approach and then like start slotting in the right place, and then suddenly it just jumped into the surface and back out again, and I was just like, what the hell? It's all gone wrong. And then Shan was like, no, what's happened is the code has guessed it's accelerating towards the surface and just pushed it too far in, and it's like, oh, so it's not doing a physically realistic step each time.
Yeah, Monte Carlo is my favorite example of that, actually, where it just moves particles randomly around the box, right? And if the energy is less, it just says, yeah, no worries, stay there. But statistically speaking, it gives you the right free energies more often than not. Just by moving particles randomly about a box, you get, even if you just move them to the other side of the box and the energy's lower, it'll stay there. And eventually, because particles are indistinguishable, you'll find the right free energy, which is a bit insane. But yeah, it is interesting what these computer programs are doing. Very much so. Like periodic boundary conditions and stuff like that. Like, what does that even mean?
Well, it took me a while to get my head around that for DFT.
Yeah, like for example, you're saying things communicate across the box. If there's a correlation of such a long length, and you have periodic boundary conditions, then you get boundary effects, which is bad. So if you're doing periodic boundary conditions, you need to make sure that anything is decorrelated before it wraps around the box.
Yeah, I've had to start doing that because we have a molecule on the surface and we want it to be isolated. And I had to keep making the unit cell bigger until we couldn't see the effect of a neighboring molecule.
Yeah.
Even though it wasn't like there was only one molecule in the cell because it was periodic boundary conditions.
Yeah.
Yeah.
Yeah,
it's like a bit of a mind sort of fuck to try and when you first look at that, I think.
Yeah, definitely. But once you get into it, like for example, if you imagine, you know, the universe that we exist in right now.
Yeah, I've heard
that is effectively a perfectly parallelized system, computationally speaking. Every atom knows what it needs to do. It doesn't need to communicate with the others. It just, when they bump into each other, that's the only time they communicate. So it's as though every atom is assigned its own computer processor, which obviously is ridiculous. But
that is an interesting way of putting it, though. Yeah.
If you could build a computer, and this is why we might exist in a simulation, right? If you could build a computer such that every atom had its own processor core, then it would be perfectly parallel. Absolutely, you could put it on a massive GPU and run the universe.
One sec, Ben. Someone just knocked on the door. I'll be back in like a second. Sorry about that.
It's all right. I've got to go soon, actually, but I hope today was useful for you. It got a bit philosophical at the end, but I think it's really important, not just because, like, of science. You know, when people talk about, like, oh, science says in the newspapers, right?
Yeah.
It's not what it bloody says at all. Well, they've done these models of COVID-19.
Yeah.
It's just, they're just lying. I think it's important for us as scientists to know what we're talking about when we say we ran this model.
Yeah, that was because I've done like the modeling stuff before. I did it in my degree, and I've been doing it for like a year and a half. It was that the discussion at the end was what I found interesting because that was sort of
because so many people. I mean, even modelers themselves and experimentalists, if they've not really sat down and thought about it, it's not entirely clear what is going on with knowledge. So it's worth reading about, I think.
Yeah, it's interesting. And tells you stories of when he's gone and spoken with like simulationists and theorists who've done things like put like a molecule in a C60 and it's like, yeah, but you can never do that in reality. And it's like the simulation said so. It's like no, cannot be done. But like,
I agree.
You always need like a simulation needs someone to ground them with an experiment.
Definitely. So this is what I have a big argument with quantum people a lot, especially their interpretations of things. So like when quantum people say, oh yeah, many worlds is true, because otherwise the maths doesn't make sense. The maths is wrong. And I'm like, well, the maths might be wrong. It's just a model.
Have you seen Devs?
No.
Oh, you should watch it. It's basically an entire program about many worlds simulation. It's really good.
Yeah, I might look into that. But yeah, like I've talked to people about many worlds, and they're like, it must be true because the maths says that other universes must exist. And I'm like, well, unless you've measured it, I don't care what the math says. It's a model.
Sorry with that. It's like, but it just if you just think about it, you go, but this just doesn't make any sense. Like, what do you mean? There's many worlds, infinite, and like what do you mean infinite amount of worlds, and like every second you got another infinite amount being. It's like this doesn't actually make sense.
Yeah, it's like because what they've effectively done, in my opinion, I'm not an expert, right? I'm not an expert, but from what I understand, and from people on YouTube who've talked about, like Sean Carroll, who's a professional physicist, right? He's got an ensemble. You know, statistical ensemble.
I've heard of it, but I've never.
Right. So statistical ensemble is an imagined set of a load of identical systems, right?
Right.
And if you assume that you've got a load of identical systems, all in different microstates, you can count up those states and get averages and stuff, right?
Right.
But that's just a trick. If you've thought up in your head a statistical ensemble, that's just a mathematical trick that allows you to do loads of experiments in parallel. So you don't have to wait for a long time. You just assume that a long time is equal to a long number of states, right? It's called the ergodic hypothesis. So when quantum people come out and talk about many worlds, I'm like, that's an ensemble. It's a thought experiment. It's not real. It's a probability distribution that's not real. You're just using it to get answers that are real, you know?
Yeah.
So, and I mean, these are the people who are pushing the boundaries of science, and it annoys me when they're like, "Oh yeah, there's many worlds." I'm like, there aren't. You haven't measured one. Unless, like, here's a portal to another universe. I don't want to know about it. You know what I mean?
It's very interesting having like a hardcore theorist sort of pointing out like the major flaws in like theory. Basically, that's I'm used to like my experimental supervisor doing that, and then my sort of Shashank the DFT specialist sort of defending it a bit more. So this is interesting, like flip around.
I put modeling an experiment on similar. Like I said, one's coming down, one's going up.
But yeah, one you do and you go explain. The other one you take and you go, can I explain it? Basically, that's why I look at it. Yeah, definitely. So if you imagine your most fundamental theory as a point, and that theory can go this way or it can go that way or it can go that way, and if this is the action, then this one might be F equals MA, but this one might be something else, and it goes all these different ways. But you don't know that that's the base of your tree. That could just be another path from something more fundamental. You can never know if you're at the bottom, ever. So whenever someone says, oh, it's true, I'm like, well, all right. It's not though, is it? Not philosophically speaking. It's not absolutely true. So. Yeah.
So that's that. Right, I'm going to have to go, but I hope you enjoyed it. I'll send everything around when it's bundled and stuff.
Yeah, it was really good. Thanks for putting it on.
See, Ben, this is why I miss being in our office together, because I get to hear all this kind of conversation.
Hey, have you been what's it? Twitch lurking?
I've been in. I came in for the modelling bit.
Did you enjoy it?
Yeah, I did. I think it was really. I think it's one of those things where, because I sit in your office, we've been over a lot of this before.
Yeah. I mean, the Python stuff this morning wasn't like, oh, here's how to do Python. It's more like, this is what Python can do.
Yeah, I scrolled back through some of the stuff and looked at the codes and stuff, and so I'm glad I came in for the modelling bit, because that's the bit I wanted to hear a bit more. And then, then you started your philosophical rant, and I was like, Ben's back. Ben's back.
Vital information. So now when Quantum and Astro start banging on about their fundamental theories, you can be like, yeah, but pics or it didn't happen.
Yeah, but Ben said.
Pics or it didn't happen. That's all I'm saying. Yeah, thanks, Matt. I agree we should play Civ 6 at some point.
We should.
But not right now. I need to go to bed.
I would play Civ 6 if you were doing that, just saying if you wanted more players. I would be down for committing however much time you want me to commit to playing Civ 6.
5,000 turns of Civ 6.
Right. Knowing you, Ben, you haven't slept for like 2 days to go to bed.
No, I slept for like
an hour.
6 hours. I did it, but Nikki told me to go to sleep last night.
Good.
At like 2 a.m.
Good.
All right, I'm gonna leave now. See you guys.
I'll see you all later.
Yeah.
See you, Matt. I'm gonna go. See ya.